Okay. Uh, Hi, everybody. Today we are going to talk about how we build and tested a motor speed controller over the last 5 laps. Our goal was to make sure a motor runs at a high speed no matter what. So our team is me, Om Panderi.
Hi, this is Hartij.
Hi, my name is Saket.
So we had three main goals for this lab. First was to build a system that keeps the motor at a speed we want. The second was to try out different ways to control the speed, like PD, PI, and PID controllers. And last was to pick the best one that does the job while meeting all the rules we were given. Okay, so here's what the motor had to do. It shouldn't go too fast at the start, like no more than 2%. It should speed up in about zero point 0.1 to zero point 0.2 seconds. It has to settle down quickly and not make mistakes once it reaches the target speed. Also, it should still work if something tries to mess with it, like an extra 5 voltage suddenly added. So we broke it down into a few steps. So in lab one, we made sure the hardware worked. In lab zero, we made sure that the hardware worked. In lab one, we measured how hard it is to spin the motor. In lab two, we looked at the electrical parts. In lab three, we tested if our math model matched the real life. In lab four, we compared different controllers. And in lab five, we picked the best one and tested if it could handle surprises. So after the first few labs, we figured out the math for how the motors behave. We also saw that it needs at least zero point 0.8 volts to start moving because of friction. So our prediction matched the real test pretty closely within like 6%. So we felt ready to start testing different controllers.
So we tested different controllers like the PD with filter, and PI, and we found out the values for KP, rise time, overshoot, and the steady state error for all these controllers. And we were analyzing on which controller to use for our future project. And we decided we're not going with the basic P controller because it only reacts instantly, but never fully eliminates any drift. And also, the customer values consistency over marginally faster response. And the change in load would forever leave a very small error in the output. And also from the test from the proportional and the PD controller, we found that the proportional controller met speed but left steady state error, and the PD reduced overshoot to zero point 0.9 and settle time to 0.15 second. But these controllers, they increased the noise by 3 times. And also they could not match the required peak voltage, which was 24 volts. And the steady state error also was not up to the required value. And we also did not go with the PD controller with the filter also because in the real world, the sensors inject noise and the derivative magnifies it, which was not our requirement. And also the required filtering complicates code and delays shipment. And also the derivative action predicts change, which is great for sharp transitions. And for the PID controller, it combines benefits of PI and PD, but it doubles the tuning parameters and the extra term risk chattering and high energy draw. We also aim for maintainability with minimal parameters, not any excessive tasks into the controller.
So, upon further discussion, we finally chose the PI controller because the integral term generally guaranteed us that the steady state error was zero. And we also found that the parameters for tuning was transparent and was easier for the future technicians to work on. And it also provided balanced performance, robustness, and simplicity. As well as the PI controller performance was meeting the rise time of 0.12 seconds, the overshoot of 1.5%, which was less than the 2%, and the settling time was also at 0.18 seconds. We also found that the steady state error was approximately zero, and we were meeting the 5 voltage disturbance without affecting any other parameters, and the voltage demand peak was at 17 volts, which was quite less than the required, but still meets other parameters. So to use the PI controller, we had to make some assumptions and trade-offs, mainly being since it was the first order plant, we just used the PI controller, but the PI controller would not be a good use if it was a second order plant. And we didn't use the derivative filter as there was no dampening. And we also chose the PI controller for simpler tuning and code, accepting the 0.02 seconds slower rise time. So what next for Solco? We thought that Solco could use these controllers for advanced driver assistance systems and drive-by-wire and brake-by-wire systems, as well as region braking systems and controls for the region braking panels in their developing cars. And the future directions that we would suggest for Solco is to developing the existing PI controllers to be used in thermal management of batteries, as well as invest in the more robust PID controllers and possibly integrate them with AI so that the second order plants can also be making full utilization of this. So that's it for today, and we are all done. Thank you.
Thank
Thank
you.
you.